The frozen core approximation. We talked already once about it, but we should mention it now again, in particular because this afternoon you're going to look a bit at it. And frozen core means that whenever you make excited determinants, then meaning you replace occupied orbitals in your Hartree-Fock determinant by virtual orbitals, then you're not going to replace the orbitals which are actually core orbitals. Now this is sort of thinking about core orbitals in atoms, but if you look at the molecular orbitals in a calculation of a molecule, some carbohydrate or hydrocarbons, you will see that for each carbon atom there is an orbital which basically only includes S basis function on that carbon atom. Which really corresponds to the 1s atomic orbital, which in a molecule still is a 1s atomic orbital, more or less. So those you would then not replace by some virtual orbitals, but you would keep them as always doubly occupied. That is what the frozen core approximation is. Carbon, oxygen. I mean, if you come to the second row, then it's not only 1s, but it's also 2s and 2p and so forth. And it gets a bit trickier when you sort of have d orbitals, 3d orbitals. Do they belong to the core or not? That sort of can be discussed, and they're actually sort of large core or small core, you could call that. Some programs doing correlated wave function calculation like Miller-Blaise perturbation theory or Carbon-Castor have this actually as a default. So if you want to include all possible excited determinants, you sort of have to explicitly turn it off. Some programs have the other philosophy that if you want to do that, because it's an approximation, you have to explicitly ask for it. As you hopefully will see this afternoon, it has quite an effect on the absolute energy, whether you include the correlation of the core orbitals or not. But the fact that they are called core orbitals sort of implies that they, going from atom to the molecule or from one molecule to another molecule, this 1s of carbon and the 1s of oxygen and so forth, they don't really change. They don't change in form, and their contribution to the energy and also to the correlation energy does not change. At least not in a significant way. And that means if you calculate the reaction or change in geometry from molecule, that contribution from those core orbitals also to the correlation energy stays the same, and therefore if you don't include it, you will not see that. You will see it in the absolute energy, but you don't see it if you take energy differences. So if you look at reaction energies, or if you optimize geometry where you also only look at energy differences, it does not make a difference. And even for excitation energies, we found out it also doesn't really make a difference. So you can use the frozen core approximation there. You just have to be aware of the fact that you might be using it because you use a program where this is the default. And if you compare with some other people or in the literature, and you get a different energy, and you say, oh, I used the same base set, I used the same geometry, I used the same method. But did you also use the same frozen core approximation or not frozen core approximation? Some programs, like the Dalton program, actually allow you also to do a frozen virtual approximation, where you can say, okay, do not want to include those very, very high-lying virtual orbitals, which are sort of the correspondence to these core orbitals. sort of the anti-bonding combination of those. That's not a lot of programs do that, and it's a bit more tricky to do that, but you could do it.